A charge Q1 equals 5.00 microcoulombs.
Microcoulombs, yes.
Is at the origin, and the second charge Q2 equals negative 3.00 microcoulombs. Is on the x-axis 0.8 meters from the origin. Find the electric field at a point on the y-axis 0.5 meters from the origin.
So we have two charges. We have charge 1 here, which is a positive charge, Q1. We have another point charge, Q2, which is located over here, Q2. They're both on the x-axis, and they are located a distance 0.800 meters apart. We are trying to figure out the electric field, which is located a distance of 0.500 meters above Q1, or on the y-axis 0.5 meters above the origin. We're trying to figure out the electric field right there. The electric field is defined by what type of charge? Electric field defined by what type of charge? Mitch.
Test charge, so whether it like...
But what kind of test charge?
Positive test charge.
One other piece about it. Yes, positive and small. So, the electric field defined by a small positive test charge. Anytime we talk about the electric field, what we're saying is, what direction would a force be on a small positive charge if I were to place it right here? So what we're going to do right now is we're going to start out by figuring out the direction of the electric field caused by charge 1 at this point. In other words, if I were to take a small positive test charge and place it right there, what direction would the force on that small positive test charge be? Please point in the direction of that force right now. The force caused right here by charge 1. You should be pointing up. I have a couple people pointing down. What would the direction be? Well, we'll do that in a minute. We'll understand that in just a second. So the reason that force would be up is why? Charlotte. Yeah, but why do they repel? So I say again? Because they are like charges. Again, because if we take a small positive test charge, and these are both positive and like charges repel, it would feel a force upward. In other words, the electric field at this point caused by charge 1 is upward. What is the direction of the electric field caused by charge 2? So now you need to think, what would be the direction of the force on a small positive test charge if I were to place it there? Please point now. Note, it's not going to be horizontal, right? It's not going to be directly to your right. It's going to instead be directly along a line toward Q2. So this is the direction for electric field 2. Why is this the direction of the electric field 2? Please, Duval.
Is that unlike charges that I attract?
So if we were to take a positive charge and place it at our point, our location here, it would be attracted to the negative charge, which would be this direction. Notice, we now have an electric field diagram. What we're going to do next is we're going to break electric field 2 into its components. After that, we're going to redraw electric field 2. After that, we're going to sum the electric fields in the x direction. We're then going to sum the electric fields in the y direction. Class, does this sound familiar?
Yes.
Sure, it does. It's exactly the same as summing the forces. We only add a horizontal line. Rather than a capital F, we have a capital E. Other than that, it is pretty much the same thing. So we're going to start out by figuring out the magnitude of electric field 1. Magnitude of electric field 1, what equation, bless you, are we going to use to get that? Hen?
The electric
is actually not going to be the electric force over Q. I do agree that that is an equation for the electric field, but unfortunately at this point we don't know anything about the electric force, so we can't really use that one. That's okay. We have what equation then, Dana, are we going to use for the electric field caused by charge 1 at this location? K times Q over R squared. And instead of just Q and R, this is Q1 because it's charge 1 and R1 for the distance from the center of charge of R1 to that point. Notice Q1 is a point charge, and we're trying to figure out the electric field around that point charge, so we're going to use this equation for the electric field around a point charge. Please give me all of these numbers. Jessica.
K is 8.99 times 10 to the 9.
Good. Times Q1.
Times Q1, which is 5.0. Oh wait, 5.0.
Talk to me. Don't do something on a calculator. Talk to me.
Oh, 5.00 microcoulombs converted into
Okay.
coulombs.
So we have an issue with that the 5 microcoulombs is not in coulombs, and we need that in coulombs. Now, at this point, we have entered second semester. You should be able to do this, and I will allow it, this one step in your head, converting from, for example, millimeters into meters, kilograms into grams, grams into kilograms, centigrams into grams, those various one steps. So at this point, you should be able to say that Q1 is equal to 5 times 10 to the what, class? Negative 6 coulombs. We can do the same thing with Q2. It's negative 3 times 10 to the negative 6 coulombs. So 5 times 10 to the negative 6 coulombs divided by R1. Jessica, what's R1?
R1.
It's okay, she's not seeing it. Who's going to help me with R1? Mitch? 0.5. Notice it's the distance from the center of mass of charge 1 to the point we're talking about in this particular case. That's 0.5. So we're going to square that, and we get the electric field 1. Could I please have some numbers? When you get it, just let me know.
179,800.
179,800. So 179,800 dimensions, please, Kraus. Newtons per coulomb. Now, that was just figuring out the magnitude, but we actually also know the direction. Emily X, what's the direction for electric field 1?
Up.
Up. You could also call it in the positive y direction. Up is fine as well. We have figured out electric field 1. We now need to figure out electric field 2. We're going to use the same equation we just used before, only replace all the 1's with 2's because we're now figuring out the electric field caused by charge 2. So it's KQ2 over R2 squared. So now, please give me all of these numbers, Mr. Chen.
K would be 8.99 times 10 to the 9. And then times Q2, which is negative 3 times 10 to the negative 6.
I'm going to stop you for a second. Now, what we're doing is we're figuring out the magnitude. We'll deal with the direction in a minute, so I'm not actually going to use that negative because we have the direction in our picture, and we're going to use that to figure out the direction. So we're not actually going to use the negative, just figure out the magnitude. Divided by R2 squared, please.
It wouldn't be 0.5.
Correct, it's not 0.5.
So then you would take 0.5 squared plus 0.8 squared, and then
Notice it's the hypotenuse, so we need to use the Pythagorean theorem to get there, right? Because this is R2, the distance along this hypotenuse. So yes, we can use a squared plus b squared equals c squared. And notice that we're actually interested in c squared or r2 squared. So it's 0.8 squared plus 0.5 squared. We don't actually need to figure out what r2 is, because what we're really interested in is r2 squared, which is 0.8 squared plus 0.5 squared. So electric field 2.
3,303.
3,000. Wait, 3,000. You mean 30,000?
Sorry, 30,303.
Point.
0.37.
That's fine. That's fine. 37, and that's newtons per coulomb. Now, the direction for electric field 2 is not as easy as the direction was for electric field 1. What we need to do now is actually break that into its components. We have electric field 2. It's right here. We're looking for electric field 2 in the y direction and electric field 2 in the x direction. We cannot quite figure it out just yet. Bless you. Why not? What are we missing? Nikolai.
We need the angle.
We need the angle. How are we going to figure out this angle? Look at
We have
We have two sides of the triangle. Notice these two thetas are the same, so if we can figure out the angle here, we can figure out the angle here. Go ahead with it. What is opposite theta? Adjacent? 0.5. In other words, theta is equal to the inverse tangent of 0.8 divided by 0.5.
57.99 degrees.
Can you give me one more?
995.
995 degrees. Okay. We now have theta. We can break this electric field 2 into its components. Please, Mr. Curry, break the electric field 2 into one of its components.
Okay, so
Bless you.
cosine equals adjacent over hypotenuse, and that equals the electric field in the x direction over the second electric field.
So electric field 2 in the x direction.
Yeah.
I don't know what to do now. I'm stuck. I'm lost. I'm confused.
Oh, cosine theta.
Ah, yes, theta, that ever important theta that so often gets neglected. Cosine of theta. So yes, we can solve for the electric field 2 in the x direction, which is the electric field 2 times the cosine of theta. Electric field 2 in the x direction then is equal to electric field 2, the 30,303.37. Should make that more clear. That's a decimal. Times the cosine of 57.995 degrees gives us what for electric field 2 in the x direction, please? I'm sorry, say that again? Let's see, cosine of theta.
Oh.
That's sad. Yes, it is. I agree with you, Meredith. In the adjacent here is actually in the y direction. Thank you much. So we have the electric field 2 in the y direction. That's why we work together on this.
16060.
16060.
0.7.
Point. Give me two more.
75.
75. Great. And that again is in newtons per coulomb. We can do the same thing with sine. Sine of theta equals opposite over hypotenuse. Opposite is the electric field 2 in the x direction divided by electric field 2. Therefore, the electric field 2 in the x direction equals the electric field 2 times the sine of theta. Notice the redundancy of what we're doing here. It's very similar to what we just did. We're just replacing sine with cosine, and or cosine with sine and adjacent with opposite. So E2 in the x direction equals the electric field 2 times the sine, oh, we just did that. Electric field 2, which is 30,303.37 multiplied by the sine of 57.995.
That's 25,697.21.
Again, newtons per coulomb. We have figured out the electric field in the x direction, electric field 2 in the x direction, electric field 2 in the y direction. To review, we drew our electric field diagram. We broke our electric field into its components. Yes, Richard?
Wouldn't it be negative for the y direction.
So what we're going to do now is we're going to do the next step, which is we've broken things into its components. The next step is what? Learn.
Redraw the diagram in terms of like its
We're going to redraw the electric field diagram in terms of its components. So Riku, it's going to be included in the electric field diagram, and when we sum the electric fields, you'll see that that negative will appear. We basically just figured out the magnitude here. I don't want to add the negative, it's in the long run it's going to confuse people. So what we do is we have the electric field 2 in the x direction, the electric field 2 in the y direction, and the electric field 1. Rather than having these 2 electric fields, we now have these 3 because we now have electric field 2 in the y direction, electric field 2 in the x direction. We've drawn our electric field diagram. We've broken electric fields into components. We have redrawn our electric field diagram. Miller, what are we going to do next?
Sum the forces, or sum the electric fields in one direction.
So we're going to sum the electric fields in both directions. Notice that summing the electric field in the x direction is just the electric field 2 in the x direction. That's the only one. So that is equal to what we just got for the electric field at 2 in the x direction, 25697.21 newtons per coulomb. When we sum the electric fields in the y direction, we get what, Mitch?
Electric field 1 minus electric field 2y.
And we have electric field 1 was our 179,800 minus the electric field 2 in the y direction, which was 160.75. We now have the net electric field in the y direction. Please. Give me 2. So we're talking 2.4. Should it 2.5? Okay.
2.6.
Right. So 2.5. So we now have the net electric field in the x direction, the net electric field in the y direction. Our goal is to figure out the net electric field, which of course is a vector. So what we have to do here is draw out the net electric field in the x direction, the net electric field in the y direction, and solve for the net electric field. How are we going to solve for the net electric field? Below? Below? Yeah, kind of.
A squared plus b squared equals c squared.
It's as simple as the Pythagorean theorem. We have a squared plus b squared equals c squared, or the net electric field in the x direction squared plus the net electric field in the y direction squared equals the net electric field that squared. Therefore, the net electric field is equal to the net electric field in the x direction squared plus the net electric field in the y direction squared, the square root of that whole thing, the net electric field then. Curry, I can't quite see them from here. Can you give me the net electric field in the x direction, please?
Yeah, it's 25,697.21.
And then that squared plus the net electric field in the y direction?
163,739.25.
That squared as well, and we take the square root. Therefore, we get the net electric field is equal to
197,539.32.
independent calculation, 197,000, etc. Just make sure.
I got 165,743.
Uh-oh.
Right.
We'll go with the second one then. Sorry, Nikolai. It's okay. Riku 165,743. That's plenty. We now can do sig figs because we're getting to the answer. So we have 166,000 newtons per coulomb. So the net electric field caused by charge 1 and charge 2 at this specific point is 166,000 newtons per coulomb. Gosh, this sounds so familiar, doesn't it? I feel like we did this in chapter 3. We need a direction, class, because the electric field is a vector. We have, bless you, the net electric field, the magnitude of it. We need the direction. We need theta. Please help me figure out theta. Rudberg?
Tangent theta equals opposite over.
Opposite is?
The sum of the force electric field y over sum of the electric field s.
The net electric field in the x, and electric field in the y. Great. So theta then is going to be equal to the inverse tangent of the net electric field in the y direction divided by the net electric field in the x direction. I have all these numbers right here, so I will just write them down. The net electric field in the y direction is our 163,739.25 divided by our net electric field in the x direction, 25,697.21. Theta, please, is equal to. Um, 81.080, yes? Great. Okay, so then with sig figs at an angle of 81.1 degrees, 81.1 degrees, Mr. Chen.
Would it be east of south? I mean, sorry, right of down? Or I don't know.
I would, at this point, I would accept using coordinate axes like north, south, etc.
Okay.
Or I would accept other things as well. Let's just give me whichever we got.
Okay, east of south?
Is it 81.1 degrees east of south?
No.
It is 81.1 degrees north of east, because we're going north from east. North of east. I would also accept 81.1 degrees above the positive x-axis. Either one, I don't really care which one you do. That is the answer to the question that they have asked. Far be it from me to stop there. Let us go one step far, well, 1.5 steps, 1.75 steps farther. Here we go. We have figured out the electric field at this specific location. Given that we have that electric field, let's take and place a proton right at that location. When we place a proton at that location, we can now figure out the electric force on that proton. That's the whole reason we can figure out an electric field, right? That electric field exists regardless of whether we put another point there or not, but we can put a charge there and figure out the force on that charge. How are we going to figure out the force on that charge? Heather.
Use the equation for electric force.
Which is?
Q1, Q2 for R's.
We could actually, but that would take us a really long time. We'd actually have to do everything that we just did over again. There's a much easier way to do it now that we figured out the electric field. Wicked.
Which the electrical field is E equals the electric force over the charge.
So we can go back to the general equation for the electric field and solve for the electric force. The electric force then is equal to the electric field multiplied by Q. So we could say the electric force equals the electric field we just got, 165,743 multiplied by the charge on a proton, which is what, Duval?
1.6 times 10 to the negative 19.
Great. So we have then the electric force.
times 10 to the negative 14.
Okay, now, bless you, with sig figs, we'll go with 2.65 times 10 to the negative 14, and notice that's in newtons, and it's at the exact same angle because it's going to be in the same direction as the electric field at an angle of 81.1 degrees, and we'll go above the positive x-axis. Now that we have the electric force, we can figure out the acceleration of that proton. How would we figure out the acceleration of that proton? Heather again.
Force equals mass times acceleration. The sum of the forces equals mass times acceleration.
Newton's second law, the net force equals mass times acceleration. The force of gravity on an atomic particle is negligible, so the only force acting on it is the electric force. So we could, I'm not going to take the time to go through and do it, but we could figure out the acceleration because this is just going to be the electric force. So the acceleration would be the electric force divided by the mass. We have the mass of a proton is 1.67 times 10 to the negative 27 kilograms. So we could figure out the acceleration. That acceleration would equal a number. Yes. We don't have to go through and figure it out. That's not the point of what we're doing here. But the question I have is, would this then be uniformly accelerated motion? Once we figured this out, we would get the acceleration equals a number. Would this be uniformly accelerated motion? Cosine.
Well, no, because as it's moving, the force is on a change.
The whole point here is that it will then move. When that proton moves, it will no longer be at this specific location, which means that this electric field we just figured out will no longer be true. The electric force will change, the acceleration will change. We figured out the electric field at one spot, right here. If this proton is anywhere else, the electric field is going to be different. Okay? So, take a moment. Did we use anything from last semester? Anything at all? In fact, the majority of what we did here was all from last semester, right? So please understand that everything you learned last semester will continue to apply second semester. In this class, we just continue to build and build and build a more accurate picture of the world around you. It's my favorite part of the class.